Hello, in our lesson today, let us discuss divergence theorem. We need a vector field AXYZ. You also call it a vector function of three coordinates XYZ, three-dimensional space. And you also need a closed surface. It's not an open surface. A closed surface which encloses a volume. Volume is V, and outward normal from the surface is in. There is a relation between the volume integral of divergence of this vector field over the volume V, and the relation is with the surface integral of A over the closed surface S. Then the relation becomes volume integral of the divergence of A is equal to the surface integral of A, and volume integral is taken over this enclosed volume by the surface S, and the surface integral is taken over the surface S, which encloses the volume V. And this relation is known as the divergence theorem. To prove divergence theorem, we have to consider this volume V. We have to draw a volume V, and in the three-dimensional, let us say we consider the Cartesian three-dimensional space, and we take a plane which is parallel to the xy plane, which cuts this volume into two halves, the upper half and the lower half. Surface in the upper half that has an equation z equal to u of xy, u is the function, and lower half the surface has the equation z equal to d of xy, d is the function of xy. And let us consider two elementary differential surface elements, one in the upper half, one in the lower half. In the upper half, n is normal to the surface, which gives the direction of the ds vector. There is a differential area vector that has the direction of n, and this is the direction of z-axis, that is the direction of k, I, j, k, three unit vectors. So this is the k direction. When we have to project this differential surface ds to the xy plane, then we have to take the dot product of n dot k. That means in the upper surface, we have to take the dot product of this n dot k. Okay, so that means ds multiplied by n dot k is equal to dx dy, is equal to dx dy, the upper surface. But in the lower surface, the k direction is here. This is k direction. That means the angle between the k direction and the outward normal is this. But when we have to project this surface, differential surface, on the xy plane, we have to include this angle, not this angle. This is, if this is theta, this is pi minus theta. That means while projecting this differential surface on the xy plane, we have to use the dot product in dot minus k. Or in other words, if you multiply ds with n dot minus k, then you will obtain dx dy in the case when we are taking the differential surface element in the lower half. So this will be very useful when we prove the divergence theorem. The left hand side, the divergence of A has three terms: partial derivative of Ax with respect to x, partial derivative of Ay with respect to y, and partial derivative of Az with respect to z. Ax here is the x component of the vector A. Ay is the y component of vector A, while Az is the z component of vector A. Therefore, totally there are three terms, term 1, term 2, term 3, and they together define divergence of A. We can take term 3 for the time being, and then using the symmetry of the result, we will be able to tell what is term 1 and term 2. Del Az del z dv, we write dv as dx dy dz and integrate one of the three variables. When we integrate this, then we obtain simply Az. And when we insert limits after integrating, then we get Az x y u. U is for the upper surface. So first we put u here, upper limit, minus Az x y d, which is lower limit, x dx dy. This minus sign has come when we have taken the limits. After doing integration, when we have substituted limits, then we have obtained this minus sign. Term in this bracket del Az del z dz, the integrand is simply daz dz dz, because when you are integrating with respect to z, then you are treating x and y as constants. That means this partial derivative here is replaced by the total derivative. In the upper half z equal to uxy, and in the lower half z equal to dxy. In the upper half, if we look at the picture, in the upper half the limit of z is uxy, and in the lower half the limit of z is dxy. So good enough. Az xy u dx dy minus az xy d dx dy. But this minus sign which has appeared here will be converted to a plus sign when we substitute dx dy in terms of ds that we have just seen. If we substitute dx dy in terms of ds, then we will obtain a extra minus sign in the lower surface. After we substitute this minus sign in the lower surface, then we obtain a plus sign here. So that means now there is a surface integral in the upper surface plus there is a surface integral in the lower surface. If we add these two, then the surface integral is over the whole surface, ds. The right hand side we get az n dot k ds. And using the symmetry, term 1 is del ax del x dv, term 1. Using the symmetry, the term 1 is ax I n dot ds. Here we have ax, here we have I dot n ds, term 1. and term 2, here we have ay, here we have j dot in ds. So three terms, axi dot in ds, ayj dot in ds, and ez k dot in ds. That means axi plus ayj plus azk dot in ds, and axi plus ayj plus azk is a, then a dot in ds. So in the right hand side, after we add all three terms, we get a dot in ds, and in the left hand side, when we add term 1, term 2, term 3, when we add term 1, term 2, term 3, we get divergence of A. Therefore, the left hand side is now divergence of A dV, and right hand side is A dot in ds. That proves divergence theorem. Now, from Wikipedia, let us look at some applications. So, let us read a little bit from Wikipedia. This is differential form and integral form of physical laws. As a result of the divergence theorem, a host of physical laws can be written in both a differential form. Differential form is where one quantity is the divergence of another. One physical quantity is the divergence of another physical quantity. For example, divergence of E Maxwell's equation. First of the four Maxwell's equations, divergence of E equal to rho by epsilon naught. One quantity is the divergence of another. And in the integral form, the flux of one quantity through a closed surface is equal to another quantity. Integral form is E dot nds over a closed surface. That is the total flux over a closed surface. That is equal to the charge, electric charge, divided by epsilon naught. This is the integral form of first equation, Maxwell's equation. In the integral form, it looks like this. So where the flux of one quantity, here left hand side is flux, through a closed surface is equal to another quantity. And also in continuity equations, divergence theorem is used. Continuity equations offer more examples of laws with both differential and integral forms, related to each other by divergence theorem. Generically, these equations state that the divergence of the flow of the conserved quantity is equal to the distribution of sources of sinks of that quantity. Look at current. Then divergence of J, divergence of the current, plus time rate of change of charge density, then the flow of net flow of electric charge from that region to another region. Here the divergence of the current in certain region of space, and this is the rate of change of electric charge, time rate of electric charge density in that region. This is equal to 0. That is the continuity equation. This is equal to 0. That is continuity equation. In electrodynamics, because if there is a rate of change of electric charge density, so in electrodynamics, this is the continuity equation. And also in quantum mechanics, there is a continuity equation where rho is the probability density. This is psi star psi. Psi is the wave function, and J is probability current density. That means that is a probability current density in quantum mechanics, and rho is psi star psi in quantum mechanics, and they follow the same continuity equation. So generally these equations state the divergence of the flow of the conserved quantity. Here the conserved quantity in electrodynamics is electric charge. And in quantum mechanics, it's the conservation of probability. Divergence of the flow of the conserved quantity is equal to the distribution of sources or sinks of that quantity. The divergence theorem states that any such continuity equation can be written. The continuity equation can be written in two forms: the differential form and integral form. The divergence theorem states that any such continuity equation can be written in a differential form in terms of a divergence and integral form in terms of a flux. So let us consider the Gauss's law and application of divergence theorem. First of the four Maxwell's equations, let us start from the first of the four Maxwell's equations. The differential form, divergence of E equal to rho by epsilon naught, and then using the divergence theorem, E dot nds is equal to divergence of E dv. This is divergence theorem. And divergence of E is rho by epsilon naught. That means E dot nds is equal to Q by epsilon naught. And if we consider a point charge, just one point charge, and enclose that point charge with a sphere of radius r, E multiplied by 4 pi r square will be Q by epsilon naught, and E will be 1 by 4 pi epsilon naught Q by r square. So I suppose that's all in today's lesson, and thank you.